Right, welcome back to part 3 of this, the second lecture in the stats part of the dyspepsia module. So we were looking before the break at a statistical test of differences called the t-test. That was for situations in which you have a quantitative measure that you want to compare between two groups. But what happens if instead you've got frequencies in categories in two different groups? Well, you're going to need a different kind of test, and it's called the chi-square test. So that's what we're going to look at in this section of the lecture. So just to remind you, the two different scenarios, the two different kinds of difference we might be looking for. We might be looking at a quantitative measure like this. In the example, it was how blue is your urine, and we might be comparing two groups and asking whether they're different. T-test works nicely for that situation. But in this situation, we, instead of having a continuous quantitative measure for each of the groups we're interested in, instead we have frequencies. It might be patient outcomes. Did they live or die? Or it might be did they have children or not? It's any variable where the answer is a category rather than something quantitative. So let's look at how we deal with this situation. Sometimes it's a bit more difficult to see what the question is, so we're going to think about how we could frame a hypothesis about frequencies. Essentially, the principle we're going to adopt is we're going to frame a null hypothesis that says there's no difference between the observed frequencies, the ones that we've actually recorded from the patients or whatever it is we're studying, and the expected frequencies under the null hypothesis. So the what we would expect if nothing interesting was going on, essentially. So the null hypothesis is that the observed data will be the same as the expected data on average, while the alternative hypothesis says that there'll be some kind of difference between what we've observed and what we would expect if nothing interesting was happening. So it's much easier to understand this with a real biological example, and I'm going to use an example that's about allergies, because you know we're having an allergy epidemic certainly in the developed world. Huge numbers of people having sometimes really life-threatening reactions to allergens. So we're going to look specifically at peanut allergy actually, and what we've got here on this slightly confusing slide is the idea that we could collect data for men and women who are having an allergic reaction or who have had an allergic reaction to peanuts and those that have not. So what we're going to look for is whether severe allergic reactions to peanuts are more common amongst men or women. And this is obviously a question that would be important if you were trying to work out how to manage allergy and treat it. If there's a strong difference between the sexes, then that's going to impact on your strategy for treating people. So the data set, although this slide looks a bit messy, is quite simple in the sense that you've just got 4 frequencies. You can measure the frequency of men that have the allergy, men that don't, women that have the allergy, and women that don't. So we get 4 frequencies, F1 to F4. And there's 2 variables of interest here. Do they have the allergy, and what sex are they? And what we're going to do in order to test our hypothesis is, so in this case our hypothesis is that sex has some kind of effect on the likelihood that you get the allergy. So the null hypothesis is going to be that sex has no effect on the likelihood you get the allergy. We need to work out what the expectation would be of these frequencies if that null hypothesis was true. If nothing interesting was going on, what would the frequencies look like? And to do that, we have to do a little bit of maths. And we're going to rely on being able to calculate the total number of people in our study who have an allergy, whether or not they're male or female, and the total number that don't, as well as the total number of men in the study and the total number of women. So these sums here in this little table down here are going to be really important in us calculating what we would expect to see in the situation of the null hypothesis. So this table might look faintly familiar. It's a contingency table, which we met in the previous lecture. So it shows us 4 different combinations of 2 different variables, and obviously you can have a contingency table that's bigger than that with more options if you want. Oops. So we're going to use the contingency table to figure out what the expected values should be. What would we expect the number of males and females with allergy and without allergy to be? So first of all, let's think about the males. We want to work out how many males should have the allergy if the null hypothesis is true. The null hypothesis says sex has no effect on allergies. If sex has no effect on allergies, then what we would expect is that amongst men and amongst women to see the same proportion of people with allergy. What proportion of people should we see with allergy? Well, the overall proportion in the population. Men and women should both reflect the population as a whole. So what we need to do is calculate the average proportion in the whole population of people that have the allergy. And to do that, we can use the observed data. We can put together the men who have allergy and the women who have allergy, add those up and express them as a proportion of the total population in our study. So if we've got 10 men with allergy and 10 women with allergy, that would be 20 in total out of a sample of, I don't know, maybe 100. So in which case it would be 20 out of 100 people have allergies overall. That overall probability of having an allergy is going to be the thing that allows us to then calculate how many men in the study we would expect to have allergies if sex didn't matter. So this is how you do that calculation. You say, well, we've got F1 plus F2 males in total. Here are all the males in the study in the top row of this table. So F1 plus F2 is the total number of males. I don't know, in this study we might have 1,000 males. And if the probability of having allergy in the whole population is 20%, then we do 20% of 1,000, and that would give us our expected number of men who should have the allergy if the null hypothesis is true and sex doesn't affect how likely you are to get the allergy. So what we end up with after this process is a contingency table of observed values, O for observed. So we've got the 4 observed frequencies of allergy and non-allergy. And then, because of our mathematical jiggery-pokery on the previous slide, we can calculate the expected values in each of these cells based on the population that we're surveying. So E for expected. And once we've got the observed data and the expected data, we can run a statistical test that measures the difference between the observed values and the expected values and then calculates a p-value from them. So this is called a chi-squared test, and it uses this test statistic called chi-squared. So chi is a Greek letter which has a kind of straight limb and a curly limb, and chi-squared is just the name for this particular statistic that quantifies the difference between observed and expected frequencies. So you can do a chi-squared test in Excel pretty easily. There's actually a function called equals chi-test in Excel. So as long as you've got the observed and the expected data, you can get Excel to tell you what chi-squared is. I'm not going to give you the equation and make you worry about calculating that yourself, for example. So here we've got the data I've been talking about in my example. We've got the observed data of males and females with allergies and no allergies. This is a big study with 1,000 men and 1,000 women, most of whom don't have severe allergic reactions to peanuts, but small numbers do. In total, 104 out of 2,000 people have strong allergies. So that's going to give us our expected value of men and women who have the allergy. So we say, well, we've got 1,000 men and we expect 104 divided by 2,000 of them to have allergy, which ends up being 52. So in this lower table, we've got those expected values calculated, and you can see that the expected values for males and females, since we've got 1,000 each of them, are both the same, they're 52. So we're expecting the same proportion of men and women to have allergy if the null hypothesis is true, and the null hypothesis says there's no effect of sex on allergy. So once you've calculated your expected values, you can then put them together with the observed values into your chi-test equation, and it will magically produce the p-value for you. So in this case, the p-value is 0.001, which is 1 in 1,000. So it's telling us that we've got a big difference between the observed data and the expected data, much bigger than we'd expect. What does it look like? Look at the table. Here are the observed data. We've got nearly twice as many women with allergy, extreme allergy, than men. And this, it turns out, is true in the population, that there is a slight bias towards women having strong anaphylactic reactions to peanuts compared with men. And it's a big enough difference that when you compare it with the expectation, which is that equal numbers should have the allergy, equal numbers of men and women, you end up with a very low p-value. In other words, the test is telling you there's a very low probability of seeing this big a difference in the allergy of men and women if there wasn't really a difference. So from that we conclude the null hypothesis is wrong. Just to note that as well as calculating the p-value, you obviously, in order to report your stats, you want to calculate the test statistic as well. Excel has done it, but annoyingly it doesn't present it unless you force it to. So what it tells you is the p-value, which is useful, obviously, but what you also want to know is the chi-squared value. So to get the chi-squared value from the p-value, you need to use another function called chi-inv, which is like the inverse of chi-squared. If you do chi-inv and you give it the p-value, it will tell you what the chi-squared value was, which is 10.39 in the case of this particular study. So the conclusion based on this very small p-value is that sex does affect the likelihood of an extreme reaction to peanuts. And that's because the data are extremely unlikely if the null hypothesis is true. So we have to reject the null hypothesis if we're using a cutoff of 0.05, and the alternative hypothesis therefore stands for the time being. This is true in adults apparently. Strong food allergies are more likely in adult women, but interestingly, apparently I think it's the reverse in children. Okay, so that's the end of this lecture. Quite a lot to get your head around there. So I think you'll find that the workshop's helpful in that you'll have a go at putting these tests into practice, which will help you remember what they're for and what the whole point is. But let's just kind of go back over the main messages from today's lecture. It's really important when you're doing analysis, you're not just doing it for the sake of it. You're trying to test an idea, and we formalize that idea as a hypothesis. And normally we have a pair of hypotheses. We have the hypothesis that says something's going on, there is a difference or there is a trend, and we have the null hypothesis that says nothing's going on here. And we use statistics to evaluate which of these hypotheses might be right, but because we're sort of inherently very conservative, what we tend to do is we focus on the null hypothesis and we say, well, we know what the data should look like if the null hypothesis is true. We can then look at the real data we've got and we can ask what's the probability, what's the likelihood of the data that we've collected if the null hypothesis is true. And if the data are very unlikely, that's evidence that we should reject the null hypothesis and retain the alternative hypothesis. So in order to actually do this in practice, we're going to need a statistical test, and we look today at difference tests. So we want to use a difference test to tell us whether the null hypothesis should be rejected. And we do that by calculating a test statistic from which we can then calculate a p-value. And we looked at the situation with a quantitative variable where we used a t-test to compare two groups, or a situation where we had frequencies that we compared with a chi-squared test, both of which give you a test statistic, t or chi-squared, and from both of those the computer can give you a p-value, an exact probability of observing those test statistics if the null hypothesis is true. And all of this is so that we can reach an objective conclusion about our hypothesis rather than simply sticking a finger in the air and saying, well, I think the data look like they show this. So, you know, all these scientists at the moment who are worrying about whether or not vaccines are effective against COVID or whether or not some particular public health measure is going to stop the pandemic, they're not relying on looking at a graph and saying, yeah, it looks like something's happening. They're actually behind the scenes doing lots of hardcore stats, and the central part of that process is calculating a p-value, which tells you how likely is it that this many patients have not got COVID when they've been vaccinated if actually the null hypothesis is true. And the null hypothesis in the case of a vaccine trial would be the vaccine has no effect on COVID. Okay, so that's me done for today. If your head is swimming with all those different test statistics and p-values, try to focus in on the key thing that I want you to learn from today. And the key thing from today is that you need to be able to formulate a hypothesis about a difference and then test it with a statistical test. That's the objective we were going for. So hopefully once you've done the workshops, you'll feel confident that you can formulate a hypothesis and then perform a test to test it. Okay, so next week we're going to have a lecture about something rather different. So today we dealt with differences. Next week we're going to look at trends. I'm always desperate for things to illustrate my statistical concepts. This is a trend which is thankfully rapidly going out of fashion. If we'd done this in a lecture theatre, I might have graced you with my attempt to do a dab, but I'm luckily not going to have to do that today on screen. But yeah, we're going to talk about trends, which are rather different from differences. But actually the concepts we've developed today are going to be useful for us next week.